In this video, I'm going to talk about which method one should use when trying to calculate volumes of solids of revolution. Sometimes people are confused about whether or not they should use the method of slicing or the method of cylindrical shells. And what I hope is that this video will help clear things up. In fact, the answer to our question depends on two things. A, whether or not the region, I've called it R here, that we're going to be rotating about an axis or a line is described as being bounded between two functions of x or two functions of y, and the method that we choose is also going to depend on whether or not our region is being rotated about a line that's parallel to the y-axis or a line that's parallel to the x-axis. In other words, depends on whether or not we are rotating about a vertical line or a horizontal line. In this first case that we're considering, we're going to assume that our region R is bounded between two functions of x. So this curve here is expressed as a function of x, y equal to g of x, and this curve here is supposed to be expressed as a function of x as well, y equal to f of x. If your region is described in terms of functions of x, what you should do is the following. Instead of viewing your solid of revolution as being obtained by rotating your entire region R all at once about a line, what you should do is begin by picking a point X. All right? Pick a point X, in this case between 0 and A, and consider the vertical line segment. The vertical line segment corresponding to x within the region R. So I've drawn that here in blue. Now, in order to obtain your entire solid of revolution in each case, what you can do is imagine that you rotate this line segment about your line that you're supposed to be rotating about, and you do this for each x between 0 and A in this case here. In this way, you'll obtain the entire solid of revolution. After you've picked your point X here, formed the vertical line segment in R corresponding to X, ask yourself, what sort of shape are you going to obtain when you rotate just this vertical line segment alone about your axis of revolution? Will you obtain a slice, which looks like a disc or maybe a washer shape? If so, you'll want to use the method of slicing. And if, after you've rotated this line segment, you obtain a cylindrical shell shape, well, then you should use the method of cylindrical shells. All right. So here is that same statement written. And essentially, what I've written here is all you need to know when your region is bounded between functions of x. So when R is bounded between functions of x, form a vertical line segment as shown. So for each x in the appropriate region, you form the vertical line segment in R at x. Now what do? Now rotate this line alone. So rotate this line about whatever line it was that you were supposed to rotate your entire region about. Think about what sort of shape you'll obtain when you rotate this line alone about the line about which you're supposed to be rotating. If you obtain a slice that looks like a disc or washer, use the method of slicing. That seems reasonable. If you obtain a shape that looks like a cylindrical shell, use the method of cylindrical shells. Well, that seems pretty straightforward. Now I'm going to say exactly what's going to happen depending on whether or not you're supposed to be rotating about a vertical line or a horizontal line. In this case here, we're supposed to rotate our region R about the horizontal line y equal to c for some number c. And what do we do? Well, because, again, our region R is supposed to be described as being bounded between two functions of x, for each x corresponding to points in our region R, so in this case for x between 0 and a, we take the vertical slice at x. And now all we need to do is think about what sort of shape will we get when we rotate just this vertical line segment about the line y equals c. Well, to see that, I'm just going to draw the reflection of this line segment and the line y equals c. What do we have? We'll get something like this. And when we rotate this line segment about y equals c, what are we going to do? Well, we're going to end up carving out, or tracing out, a slice that looks like this. And this looks like a nice washer shape. So, in this case, we should use the method of slicing. So, if we want to be very specific, we can write that out. So here it is. You can write this down if you want. When R is described in terms of functions of x, as was the case here, R was bounded between two functions of x, y equal to g of x and y equal to f of x. When rotating about a horizontal line y equals c, for example, the x-axis, you can use the method of slicing. I wouldn't actually memorize that myself. What I would do is I would remember that because R is described in terms of functions of x, I would take the line segment, the vertical line segment corresponding to a point x in our region, and I would rotate that line segment alone about my horizontal line, possibly the x-axis, and I would look and see what sort of shape I got. What I would notice is that I'll always get a nice slice. In this case, I ended up with a washer shaped slice, and so I'd use the method of slicing. Notice that because our region R is described in terms of functions of x, when trying to find the area of this slice, which is what I would want to do when using the method of slicing, I'll be able to find this distance here in terms of x. It's going to be the distance from c to whatever this y value here is, which is going to be f of x. That distance is c minus f of x. And I'm also going to need to know what the radius of this large disk is, the outer disk that we can see here. And that's going to be the distance from c down to whatever this y value here, which is given to us in terms of x. It's namely g of x. So that radius right here is going to be c minus g of x. All right? That will allow me to compute a of x for each x, in this case between 0 and a. And to find the volume, we would integrate a of x times thickness dx from 0 to a. Now in the second case, we're assuming that we're supposed to rotate our region R, which is again described as a region bounded between two functions of x, about a vertical line, in this case, x equal to c. So to determine what method we should use, again, because our region is described as being bounded between two functions of x, I consider the vertical line at x for each x between 0 and a in this case, and I think about what sort of shape will be traced out if we rotate just this line segment here about the line x equal to c. And what would we get? Well, if we rotate this line segment about x equals c, what do we get? Well, I'm going to draw the reflection of this line here in x equal to c. It's going to look like something like this. And because it's rotated, I'm going to draw something like that. Okay, so if we rotate the vertical line segment at x in R about the vertical line x equal to c, what do we get? Well, we get a cylindrical shell shape. So in this case, we should use the method of cylindrical shells. Let me write that down. So here it is, and you can write this down if you like. It says, again, when R is bounded by functions of x, as was the case here, and rotated about a vertical line x equal to c. So for example, when x is 0, we're talking about a rotation about the y-axis. Well, in this case, you can use the method of cylindrical shells. How would I actually remember this? I wouldn't memorize all of this. Again, all I would remember is that because R is described in terms of functions of x, I will consider vertical line segments at x for each x corresponding to points in our region, in this case x between 0 and a. I consider the vertical line segment, and because we're rotating about a vertical line segment x equal to c, I'll just rotate this single line about x equals c, and we'll see what sort of shape we'll get. And what will we get? Well, we'll get this cylindrical shell shape. That's why we would use the method of cylindrical shells. Notice that because our region is described in terms of functions of x, we'll be able to calculate the volume of each of these cylindrical shells. How is that? Well, what do we need? The volume is going to be equal to the circumference times the height. The circumference, in this case, is going to be 2 pi times the radius. Well, that's going to be the distance from this point here, which is c, over to x, so 2 pi times c minus x. And then times the height is going to be the distance from this y value to this y value. We know what these y values are at x because our region is described in terms of functions of x. So it's going to be the distance from f of x to g of x, which is f of x minus g of x. So that'll allow us to determine dv. We'll have one shell for each x between 0 and a, and so we'll integrate dv for x between 0 and a. We'll integrate with respect to x then from 0 to a. So now we're going to assume that we're dealing with a region R that has been described to us in terms of functions of y, not functions of x as we had before. So if our region is most naturally described as being bounded by two functions, x equal to f of y and x equal to g of y, what do we do? Well, in this case, for each y corresponding to a point in R, we're going to consider the corresponding horizontal line segment in R. So let's draw that. So taking a y, in this case between 0 and b, we draw the horizontal line segment in R corresponding to y. Now, all we're going to do is think about what sort of shape we're going to get in this case when we rotate our horizontal line segment about the line that we're supposed to rotate our entire region R about. If, when we rotate our horizontal line segment, we obtain a slice, which looks like a disc or maybe a washer, then we'll use the method of slicing. If, when we rotate our horizontal line segment, but the line that we're supposed to be rotating R about, we obtain a shape that looks like a cylindrical shell, then we'll use the method of cylindrical shells. And that's really all we have to remember. So let me write that down. Okay, so here it is. And you can write this down because this is, again, essentially all that you need to remember. When the region R that you're considering is bounded between functions of y, as we have here. So here, R is supposed to be described as being bounded between the function x equal to f of y and x equal to g of y. In this case, when your region is bounded between functions of y, form horizontal line segments. In particular, form the horizontal line segment at y as shown. So for each y corresponding to a point in R, in this case y ranges between 0 and b, we form the horizontal line segment at y. Now, what do? We rotate this line alone. Rotate this line alone. If, after rotating this line alone, you obtain a slice that looks like a disc or washer, well, use the method of slicing. On the other hand, after you rotate this line segment alone, if you obtain a shape looking like a cylindrical shell, use the method of cylindrical shells. And again, that's really all that we need to remember, but I'll now be more specific and say exactly what's going to happen depending on whether we rotate our horizontal line segment about a horizontal line. Well, you can maybe see already based on what we did before that you'll get a cylindrical shell, and what shape you'll see if we rotate about a vertical line. You can probably see already that you're going to get a slice that looks like a washer, and so in this case we would use the method of slicing. But let's be very specific and actually deal with those two cases now. Okay, so we're going to suppose first that we're going to rotate our region R about a vertical line x equal to c. And again, in this case, we're assuming that our region R is described in terms of functions of y. All right, so as before, for each y corresponding to a point in R, in this case y is going to range from 0, the origin, up to b, we form the horizontal line segment at y. What are we going to do? We're going to rotate this line segment alone about the line x equal to c and see what sort of shape we get. If we get a cylindrical shell, we'd use the method of cylindrical shells. If we get a slice, we'd use the method of slicing. In this case, as we'll see, we're going to get a slice. So let's draw it. So rotating this line about x equal to c, what do? I'll just draw the reflection of this line here in x equal to c. You can imagine what's going to happen as this line segment rotates about x equals c. What are we going to get? Well, we're going to carve out a nice looking slice that looks like a washer. So there we have it here. So when we rotated this horizontal line segment at y, which we did because our region was described in terms of functions of y, we got a nice washer shape. So this will be a good method. This will be a good situation, rather, for us to use the method of slicing. So let's write that down. So here we are. You can write this down if you want. It says that when r is bounded by functions of y, as we had in this case, r was bounded by x equal to f of y and x equal to g of y, and r is rotated about a vertical line, x equal to c, for example, when x is 0, we'd be talking about rotating about the y-axis, you should use the method of slicing. Well, again, this isn't something that I would memorize. What I would try to remember is that if r is bounded by functions of y, what can I do? Well, for each y corresponding to a point in our region R, in this case y between 0 and b, I would form the horizontal slice at y. I would rotate that line about, in this case, the vertical line x equal to c, and I would see what sort of shape I get. And what I would see is that I would get a nice slice that, in this case, looks like a disc. So, because I got a nice slice, I would use the method of slicing. Note that this is going to work out well because r is described in terms of functions of y, and so if I wanted to use the method of slicing, I'd need to know the area of the large disk. For that, I would need the radius of the large disk. That's going to be the distance from x equal to c to whatever this x value right here is. And I know what this x value is because this x is just equal to g of y. That's because r was described in terms of functions of y. Similarly, I'm going to need to know what this radius here is. And, well, it's going to be the distance from x equal to c to whatever this x value right here is, and I know what that is. This is x equal to f of y. All right? So the distance from here to here then would be c minus f of y, and the distance from here to here, this large radius, would be c minus g of y. Now finally, for our last case, we're going to assume that our region R, which as before is bounded by functions of y. So R is described in terms of functions of y. In this case, well, as before, we're just going to take the horizontal line segment in R corresponding to points y, in this case for y between 0 and b, and we'll take our horizontal line segment and we're going to rotate it about our horizontal line y equal to c. And we'll look to see what sort of shape we get. And what will we get? Well, I'm going to draw the reflection of this line here. And y equals c, and what are we going to get? It's going to look like this, I guess. Something like that. And like this. And what we see is that if we rotate this horizontal line segment about the horizontal line y equal to c, we're going to obtain a shape that looks like a cylindrical shell. So, in this case, we're going to use the method of cylindrical shells. Let me write that down. So here it is. It says that if R is bounded by functions of y, as is the case here, so if R is described in terms of functions of y, maybe just one function of y, a constant, So here we are. X is equal to f of y is this curve here. X equal to g of y is supposed to be this curve here. And r is rotated about a horizontal line, in this case, y equal to c, might, for example, be the x-axis. If c were equal to 0, what should you do? You should use the method of cylindrical shells. Again, this isn't something that I would try to memorize. I would just remember that if r is described in terms of functions of y, I should take all points y corresponding to points in r, in this case y between 0 and b, and form the horizontal line segment in r at y. Then rotate just that horizontal line segment alone about our horizontal line y equals c in this case, and look to see what sort of shape you will trace out. In this case, you will trace out a shape that looks like a cylindrical shell. Therefore, you should use the method of cylindrical shells. Note that because our region R was described in terms of functions of y, we'll have all the information to calculate the volume of this shell in this case. What are we going to need? Well, the volume of the shell is going to be equal to the circumference times this height here, and then times a thickness dy. Well, for the circumference, we're going to need to know the radius of this base here. That's going to be the distance from y equals c to this y value here. Well, that's just going to be c minus y. All right, we're also going to need to know what is the height of this rectangle here. Well, it's the distance from here to here, which is the distance between this x value and this x value. We know what this x value here is. It's just equal to f of y, because this curve here was described as a function of y. And we know what this x value here is. It's just going to be equal to g of y, because this curve here was described as x equal to g of y. The distance then from f of y to g of y is just going to be f of y minus g of y. All right. Note as well that we're going to have one cylindrical shell for each value of y, in this case between 0 and b, and so we would integrate from 0 to b. One last point. Sometimes people might think we should integrate all the way from 0 up to whatever this y value up here is, but no, we should integrate just from 0 to b, because we have one cylindrical shell for each y between 0 and b. Putting all those cylindrical shells together, we will get the entire solid of revolution obtained when we rotate all of r about the line y equals c. That's all.